Welcome, everyone. I'm Ken Medlock, speaking to you from the Baker Institute. It's a pleasure to actually be in the office again. As many of you might know, Rice was virtual only for the first couple of weeks of the semester, but we're actually back live and in person. Of course, I'm in my office alone, so I don't have to wear my mask. But for those of you who get a chance to come to campus, we'd love to see you, as long as you're wearing a mask. That is the rule on campus. But anyway, it's a pleasure to be here today and kick off today's conversation and, quite frankly, our series of webinars for the year with a really robust discussion of energy transitions and the technologies that are needed to really accelerate the pace of change. I'm really pleased to have with me today Dr. Pradeep Venkataraman. He's with MHI. I'm going to let him introduce himself in just a few minutes. But I want to say a couple of words just about the subject. Energy transitions are becoming really the norm in any conversation around energy and environment lately. And the manner in which energy systems transition is certainly on lots of folks' minds. Up and down the energy value chain across energy sources, it doesn't really matter. It is a centerpiece of the conversation. And understanding the complexities of what is required for energy transitions to occur, which is going to be, very diverse, quite frankly. It's going to be different in different regions. It's going to look different in different regions. There'll be different policy measures that are adopted on a regional basis. But the end goal is ultimately a lower carbon energy system. And so we had a really interesting conversation. Gosh, I'm going to go back to our annual conference, which was in October of last year, beginning of October of last year. Kazuki Satomori from IEA talked about their net zero scenario to 2050. And one of the things he said that struck a lot of folks, because I don't think they realized it just based on the headlines around the release of that report, is that upwards of 46% of the technological innovations that are required to meet the scenario they laid out are not known today. And that's a really stark reminder of the importance of R&D and innovation. And that's really going to be the centerpiece of our conversation. And a lot of what we talk about today will focus on hydrogen in particular, which is a great topic for those of you who are in the Houston area, quite frankly, because there's a lot going on here on the hydrogen front. There are various initiatives ranging from things that are going on at the City of Houston, at Port Houston, the Greater Houston Partnership, work going on with some of my colleagues at the University of Houston, work being driven through the H2 at Scale project by GTI and the University of Texas, the Center for Houston's Future. I could go on and on and on. There's a lot of different groups that are looking at hydrogen and all of the complexities involved in scaling it. But the one thing that's really interesting about hydrogen in the context of Houston is there's already a hydrogen market. It's relatively small. And when I say relatively, relative to other energy sources, but it exists. So there's a core infrastructure that could be leveraged to really facilitate change and expansion. And I think that will probably come up in our conversation today as well. So what I'd like to do now is welcome Pradeep to the floor. And Pradeep, if you could take the mic and tell everybody a little bit about yourself, and we'll get right into it.
Thank you very much for having me here, Ken, and I'm very happy to kick off this first webinar of virtual fireside chat. It is cold. It's been cold, a little bit cold over the last few weeks here. So sitting by the fireside would have been nice, but this will do for now, given the pandemic. I would like to also welcome the audience and who have joined us, and I hope they have some good takeaways in terms of hydrogen as well as energy transition in general. To give a little bit of background about myself, I'm a chemical engineer by training. I have a PhD in chemical engineering, and my career has, in a sense, followed the energy transition in some sense. I represent a corporate function called Investment and Business Development at Mitsubishi Heavy Industries America. And that gives me a unique perspective to, or I would say I'm at an intersection of looking at innovation in the field of energy transition and also the investment that's required to upscale it. So with that perspective, I hope I'll be able to add some new information or new knowledge to the ongoing conversation in and around energy transition. I have worked previously with super majors, ExxonMobil and Baker Hughes, as a technology developer. So from being a technology developer to a technology integrator and technology assessment has been my career trajectory. And past 2 to 3 years, I've been looking at hydrogen, ammonia, and carbon sequestration value chains.
Excellent. There's a lot there. There's a lot going on there, actually, that is germane to this discussion, without a doubt. I'm sure we're going to pull on every single one of those threads, because ammonia and carbon capture definitely have intersections with hydrogen, which I'm sure we'll explore. Just to kind of get us going, and I want to drill in on hydrogen to start. Can you just give everyone, just as a level set, a short explanation of hydrogen as an energy source from production to storage to transportation all the way to end use?
So thank you very much for breaking it down that way, because when you look at any energy value chain, you actually look at it in three different parts: the production, transportation and storage, and the end use. To give you a brief analogy for that, you would have crude oil being produced and refined to produce gasoline, and how gasoline gets, or crude oil gets transported around the globe from where it's produced to where it's used, and then how it's stored at a gas station or a refinery, and then finally dispensed. The thing that most people do not realize, that energy value chain is not just transportation or power. It actually cuts across several different cross sections. Power, transportation are important, but also industrial heating and commercial and residential sectors heating and are also part of this big equation. Now, to talk about hydrogen, and at the risk of dating myself a little bit here, this is not the first time we are talking about hydrogen. Way back, as a matter of fact, my first PhD research project was storing hydrogen, and it was driven by a DOE mandate of looking for materials for storing hydrogen. Now, the conversation at that point of time was slightly different, because hydrogen was primarily being considered for a transport purpose. But the imperative has changed as of today, and much water has flown in Mississippi. We have been through shale boom and several other geopolitical events over the course. But this time around, it's slightly different for primarily three different reasons. One is, and this one can actually refer to Future of Hydrogen that came out, publication came out from IEA in 2019, and kind of lays it out in four different ways. I'll highlight the three. One is the climate imperative, right? There is, and both public sector and the financial sector being very aware, and it's more driven from a shareholder's perspective. The imperative is being driven that way. The market is driving the imperative towards climate change. The second is energy security, and a lot of economies are looking at enabling energy security and reducing their dependence on fossil fuel. And the third one is the change that has come in terms of penetrations of renewables and cost reductions in wind and solar over the decade. And there's a lot of learnings that the market in general has taken from how to scale these. So that's the different situation, and that's why hydrogen is part of a conversation in a different sense. Now, to describe hydrogen as a fuel, it's been, as I said, it's been around for a long time. It's the most abundant element in the universe. And it has a fairly high energy calorific value in terms of per unit mass. The problem is it's also the lightest element. And that's why when you look at it in a volumetric sense, it actually has a very low energy density. That means you really have to compress the gas or liquefy it to get this, to be able to transport significant amount of energy, quantum of energy across the value chain. For the uninitiated, a easy thumb of rule is 1 kg of hydrogen, 1 kilogram of hydrogen is roughly the same amount of energy as 1 gallon of gasoline. And so when we talk, but in terms of volumetric density, it's 3 times lighter than natural gas. So you can imagine the factor of compression that is required, and that again is a parasitic energy load. So to address your previous laying out of the 3 different parts of the value chain, there are production technologies as of now. We do produce hydrogen. Hydrogen is primarily used as feedstock, industrial feedstock for ammonia in refineries, and also for chemicals productions. Hydrogenation. It's also used for reduction of iron ore. In addition to that, so there is a way to produce hydrogen. Electrolysis has also been around for a long time. On the end use side, as I said, it is being used for mainly as a feedstock, but also as a fuel for rockets, right? So the reason I'm bringing this up is there is technical know-how on how to handle hydrogen. It is not a new thing. The problem is to be able to do this in a more economical way. And I'll highlight that as we go through the conversation later on. The missing portion is the transportation and storage, right? That's the most critical part that is kind of as a impediment for transporting hydrogen in its native form, is kind of a more uneconomical, or I wouldn't say uneconomical, but expensive because of the reasons I cited of energy density. And so that is the roadblock right now if you look at the hydrogen as a value chain.
Yeah, so that's actually interesting, because I know there's a lot of exploration into ways to overcome that potential impediment, that cost impediment. And one of them is the use of a different carrier. So in many ways right now, a hydrocarbon molecule is a hydrogen carrier, right? So I know there's a lot of the issue, of course, is once post combustion you end up with the carbon. So there's a lot of interest in ammonia, which is moving, to a nitrogen-based carrier, and there's also a lot of interest in, high compression, sort of, in some cases cryogenic movement of hydrogen in different forms, sometimes on pipelines. Storage also comes into play here, because when we think about some of the applications that have been proposed, particularly on the green hydrogen front, and I'll just use the colors for everybody's benefit here, but when we talk about green, we're talking about a renewables-based hydrogen production platform where you use wind or solar to drive an electrolyzer, right? And you get hydrogen. But at the end of the day, if you're going to generate hydrogen when you've got excess renewable power, you've got to be able to store it so that it's usable either in power generation or, in some other application. So I wonder if you could do a couple of things here. This is kind of a long-winded way of asking this question, I guess, but could you talk a little bit about hydrogen's potential in different storage applications and what's being researched and looked at right now, and how that can facilitate either balance in electricity markets or applications beyond electric power into transportation, et cetera? Because I think you did a good job of commenting on the cost reductions on renewables. So this is one that's definitely in play now when we talk about the green hydrogen pathway.
Well, thank you for that question. So Ken, before that, let me actually give you some statistics, okay? Just so that. So right now, United States actually produces 15. So you mentioned that in your opening remark, but I just want to put the numbers out there. Is 15% of global hydrogen is being produced in the U.S. And about 4 million metric tons is produced right here in the Gulf Coast every year. And that's about 40 to 60% of merchant hydrogen. When I say merchant hydrogen, that's not in situ production and consumption, but actually produced as an industrial gas. That's about 40 to 60% of the entire global hydrogen merchant production. So that also puts Houston as a hydrogen hub, right? Or a hydrogen hotspot. Let me use that word. And so we have a lot of technical know-how in that sense. So that aside, I'm going to come back to your remark about different way of storage. So when we look at near-term usage of hydrogen, one of the things that hydrogen can play a very important and critical role is actually balancing the power sector, right? So you have a lot more penetration in the renewables. You have a lot of curtailed electricity that's available. And so what do? Do you have a really giant supercapacitor and really giant battery storage? It's not possible right now with the current technology. And hydrogen comes in as a giant battery. If you have the right geology, you can essentially use hydrogen as a battery for storing, for seasonal storage of this curtailed electricity. I would like to highlight one of the examples, and this will probably be the largest hydrogen storage project in the world. This is the Advanced Clean Energy Storage Project, which MHI is a part of in Utah. So essentially, you have these large salt domes, which are used as storage. And to just give you a picture of what it looks like, is each of these salt caverns about the size of Empire State Building. So you can actually store a copious amount of hydrogen. And what would happen, the whole process, if you want to look at it, is the excess electricity, renewable electricity, would be converted to hydrogen using an electrolyzer, and that would be stored inside the salt cavern. And when you need the excess demand, when the sun is not shining or when the wind is not blowing, you need to meet that peak demand, this hydrogen or seasonal demand, you can burn this hydrogen in a gas turbine, produce clean electricity, and put it back onto the grid. So hydrogen can do a fairly good, play an important role in balancing the grid, balancing the renewables, and the part of this as a storage itself. Now, how do you store hydrogen in the value chain? That's the second part, and it's slightly different from what I just described. So how do you carry hydrogen? Before answering that, let's divide the world or divide the geography into countries or locations that have and that does not have, right? So there are locations that have the combination of renewables, water, geography, geology. So, for example, United States or Chile, where you have excess renewables, but there are countries, Europe or say Japan, where you don't have the green hydrogen, availability of green hydrogen. So there has to be a network to be able to produce someplace and take it someplace. And that's where what we call as energy vectors or hydrogen vectors come into picture. And right now, you can broadly divide it in three different ways. You can either carry hydrogen as in its native form as liquid hydrogen. So you would essentially have liquid hydrogen carriers like LNG carriers. The first of one is being built and is being piloted right now between Australia and Japan as a demo. But we still don't know how the economics of this. Liquefaction of hydrogen itself is an expensive undertaking. It takes approximately 10 kilowatt hour of electricity per kg of hydrogen liquefied. So there's a parasitic load to liquefaction. The second way of looking at it is actually carrying it in as LNG itself, right? So methane can be a carrier for hydrogen. But in that case, when you transport it to the use location, you would have to capture the carbon If you're producing it through a SMR or a ATR, let me expand that, steam methane reforming or autothermal reforming, but then you have to establish a pathway for the carbon dioxide. The third way of looking at it is in non-carbon based carriers, such as ammonia, or even carbon-based carriers like liquid organic hydrocarbons. So essentially here, the difference between LOHC and ammonia is ammonia, you can take ammonia and combust it directly, or you can crack ammonia in which you'll produce nitrogen and hydrogen, and you can use the hydrogen for the purpose intended. In case of LOHC, it's a molecule that has to be transported back, and you will have to hydrogenate and dehydrogenate. So that's a two-way pathway in that particular case. We are also seeing some research. I mean, this has been going on for some time as solids storage of hydrogen, but there are several challenges on solids, of even transporting solids over long distances and handling of them, and amount of hydrogen that you could store in hydrogen as solids. So there are challenges in those, but there are active research going on.
You actually raised a couple of interesting points, and we had a couple of questions come through that I think are relevant to answer right now. But one of the points you raised had to do with networks and long distance transit for a hydrogen molecule or a converted hydrogen molecule, right? And you mentioned ammonia. You mentioned, of course, cryogenic process where you move liquid hydrogen. What's really interesting about that conversation, that part of the conversation is, and I hope most people understand this, is when you think about the Gulf Coast in particular, because you also referenced Houston being a hotspot, right? Not really a hub yet, but a hotspot. You're talking ultimately about infrastructure and logistics, and those types of things are really at the core of why Houston is known as the energy capital of the world. So it's really kind of painting a picture that for those of you who are in the Houston or Gulf Coast region and are looking for opportunities, I think this is, this should definitely be in your scope. So a couple of the questions that came through that are really interesting. One is just real simple. Somebody had a question about the name of the project you guys are involved in Utah. So if you want to give that answer, I'll move to the next one.
It's called Advanced Clean Energy Storage, ACES. This is Mitsubishi Power, 100% subsidiary of MHIA, and we are working with Chevron and Magnum on this project. Magnum is the developer.
Yeah. And the other one is really, it's more technical. So, I mean, we all know when you combust anything in the production of power, there's an efficiency loss in the conversion. And somebody basically had the question, what are the losses associated with, converting, generating the hydrogen, but then converting it back to electricity through combustion in a gas turbine, for example?
So even from the generation perspective, let's assume different. So it's actually not a straightforward question to answer, because it depends essentially on the pathway of production, right? So right now, if you look at electrolysis, let's just take the green hydrogen for the time being. You can go anywhere from 60 to 70% efficiencies for production of, in terms of how much electricity you're consuming versus how much energy you're producing. From the combustion efficiency, the current gas turbines that are there actually can combust hydrogen at 30% with, we do have gas turbines that can actually combust a mixture of 30% hydrogen and 70% methane at the same efficiency levels that you would have in a natural gas turbine. The motivation here is to burn 100% hydrogen, and the timeline we see sometime in the middle of this decade, we'll be able to have with the same efficiencies. But the challenge mainly with hydrogen combustion is the combustor itself, right? And the temperature of combustion for hydrogen is higher than that of methane. And what that means is if you're using air to produce as a source of in the combustion, instead of using just oxygen, you would produce a lot more nitrous NOx, oxides of nitrogen, which is not good for it, again, because of it can cause acid rain and all that stuff. The easy thing is to, and it's not a problem that cannot be solved, because you can actually put something at the back end, have catalysts that can take care of, which we do even now, reduce the NOx emissions on natural gas. But there is active development in terms of modifying the combustor so that you have dry, low NOx production of or combustion of hydrogen. So that's in development, and we aim to achieve that in a couple of years, commercially available 100% hydrogen combustion in gas turbines at the same efficiency levels that you have for gas turbines, so with natural gas.
Okay, but before we move on from the storage question, because this also came through, and it's a good one, the efficiency of storage. How is the hydrogen actually stored, particularly when you talk about salt caverns? And what's the efficiency? Typically, like with natural gas storage, there's a base level you've got to fill up to maintain pressure in the reservoir, and you've got a working level. How does it actually work with hydrogen?
So, along the same principles, but there are. It depends on the type of the salt dome, or if you're using a rock reservoir, that's a different scenario. But you do have to have certain pressure, which also again depends on the salt dome itself. It can vary from 200 bar to 300 bar. You have to, of course, compress the hydrogen and put it in there, and a lot depends on the geology. So I cannot give a straightforward answer. Depends on geology to geology on the pressure that is required as a cap pressure for that particular reservoir. Maybe we can take this. I mean, if the audience needs more answer, the person who's asked, they can contact us and we can give more details on this.
Yeah, absolutely. Thanks for that offer. One other question related to specifically the Utah project. Is there anything unique about the salt caverns in Utah that make this, a promising venture, or can this be applied in other places? I actually know the answer, but I'd like for you to say it. So.
The answer is it can be applied. It's actually been applied way back in 1972. I think in UK Teesside, they had the first salt dome hydrogen storage. And there are several, in Texas, we are, very close to Houston. We are sitting on top of a huge salt dome here itself. We are in process of, so we have also have a partnership with Texas Brine, and we are looking at such storage, not only in Texas, but also in the northeastern part of the United States. So there are going to be several different locations where such storage sites would come up. And in that sense, the United States is really blessed with the geology that can support this. This is not possible everywhere in the world, but United States, definitely, there are several different places where you can do this.
Absolutely. And yeah, thanks for that answer. And just for everybody's benefit, storage is an incredibly important part of scaling of a commodity market in general, particularly energy commodity market, because energy demands fluctuate on a seasonal basis, on a daily basis, and being able to accommodate those fluctuations with something other than just-in-time production is critical, actually, for hub services to emerge, and actually seeing depth emerge in a market and liquidity, so that you've actually got something that's a little bit more robust. But that point applies to any form of hydrogen, really. It's not just green hydrogen. We've kind of dominated discussion so far. So I wonder if you could maybe expand the conversation to the other area that a lot of folks are looking at right now in all different parts of the world. There's some active pilots ongoing in Europe, a lot of interest in the US in the blue hydrogen, and certainly we can't forget turquoise. MHIA is involved in one of those, but blue hydrogen is interesting because it also requires the development of another critical market and critical infrastructure, which is it involves carbon capture. So maybe if you could expand on that a little bit.
Right. So I'm glad that you brought it up, Ken, because whenever I get into a conversation about energy transition, I always say that the operative word in this whole conversation is the transition. And right now there are technologies that are different stage of maturity, and you would see uh, so to enable the transition, I think blue hydrogen also has a role to play, because there's an existing infrastructure that supports this, and we should be able to leverage that. Uh, so typically, just for the benefit of the audience, right now most of the hydrogen that's produced in the world, what is called gray hydrogen, right? And it's essentially by either steam methane reforming or autothermal reforming of hydrogen, and that produces hydrogen and carbon dioxide. If you capture that carbon dioxide, the resultant hydrogen is called a blue hydrogen. Now, there are different shades of blue depending on where you are capturing the hydrogen in the process. In the SMR process, there are 5 different places, at least that I know of, that you can capture hydrogen, and that would put the color more towards blue as you capture more. Um, the main the problem there is, again, you need to if you're capturing the carbon dioxide, you are establishing a new you have to establish a pathway for the carbon dioxide to go, right, either for geological sequestration or for utilization. And the reason I'm bringing this up is because I want later on go on to the roles that that I see in playing hydrogen will play in the near term. The other thing that you touched upon is the turquoise, right? And that essentially is the hydrogen that's resultant of methane pyrolysis. When you say pyrolysis, you're essentially heating the molecule up in absence of air. So there is and breaking the molecule up. So if you take methane and you break it down, it breaks down into carbon and hydrogen, right? And so the hydrogen that's produced is called a turquoise hydrogen, and the carbon essentially is a solid carbon. Now, there are different ways to do pyrolysis too. It's not just one single way to do it. You can either use catalysis, you can use microwaves or microwave plasma, or you can use a thermal plasma. MHI actually has, from the IBD team that I belong, we made investments in 2 companies, Monolith Materials and C0. So one is Monolith Materials recently received a grant of $1 billion conditional loan. Sorry, I would say not grant, but conditional loan from DOE for expansion of turquoise, their facility for producing turquoise, or rather they would prefer to call it green hydrogen, because if most of the carbon that's produced in the process, actually all of the carbon that's produced in the process is solid carbon and carbon black that could be used in the tire industry. That actually is a commercial grade carbon that goes into tires. So this is a particularly interesting case because it is addressing 2 different sectors, right? Yes. One that's producing hydrogen, and then the second one is it's actually producing carbon black, and that is carbon black right now that goes into tire is produced from pet coke, right? And so that's a very carbon intensive process, and so you're essentially addressing that sector. 25% of every tire essentially contains carbon black, and you're now producing it in a much cleaner fashion. The other one is the molten catalyst reactor, the C0 technology, where you're producing hydrogen and carbon, which is more amorphous and can be used as a landfill or for composites. So again, you are actually fixing in a way of thinking. If you want to think about it, it's pre-combustion carbon capture in some sense, where you're actually producing carbon as solids. Now that I said that, you're addressing 2 different sectors with this, right? And that's the reason I mentioned that is because I want to say that the role that hydrogen would play in the near term that I see. And one of the areas is the sustainable aviation fuels, right? Aviation sector right now, they have from COSIA, they have imperatives to reduce their emissions. And this is one of the difficult sectors. You can't have batteries on, on aircraft going really long distance. We don't have that right now. We don't have the infrastructure to put ammonia or even technology to burn ammonia in an aeroderivative engine for aircrafts, right? So what is the alternative? The alternative is essentially to have fuels that are produced either from biological matter or what we call as electrofuels or drop-in fuels, right? So essentially what you're doing is you're combining CO2 and hydrogen to produce, so you're now going the reverse way. In the previous case, you were breaking methane to produce, in the SMR process, you were producing, breaking methane and producing hydrogen and carbon dioxide. Now you can combine these two to actually produce liquid fuels. And that's what makes it really interesting when you think about these hubs where you have a source of carbon dioxide and a source of hydrogen. It kind of, you can leverage that to produce both electrofuels or biofuels, bioethanol. There are several different pathways to utilize both carbon dioxide and the hydrogen. And this I see as one of the potential near-term applications where hydrogen will play a very critical role. Even if you are producing biodiesel, you need hydrogen for upgrading. A lot of these biofuels, vegetable-based fuels that are being produced need hydrogen for upgrading of the oil to be able to meet the standards for aviation fuels. So hydrogen will play, if not in its native form, will play a critical role in decarbonizing these sectors like aviation and marine fuels and of course, we have not touched upon the other areas like ammonia production, as well as looking at industrial heating. So these are other sectors that I think in near terms that hydrogen will play an important role. But this is the reason turquoise hydrogen becomes very interesting, as you said, is it is multiple sectors that it is addressing simultaneously.
Yeah, you raise an interesting point, and you mentioned actually when we referenced blue hydrogen, and you need a network to handle the carbon dioxide, right? So either as direct injection into a subsurface saline aquifer and use enhanced recovery techniques, or some other use proposition. And to me, that's what's really interesting about what you're seeing in the turquoise hydrogen space is there's a lot of existing application, but tremendous amount of research, some of which is going on here at Rice, right? On how to create value propositions from that solid carbon that's captured through advanced materials, et cetera. So that, when we talk about the economics of everything, that's game changing, right? Because now you're not talking about just a waste byproduct. You're talking about something that's an intermediate feedstock into something that has value. So it has the potential long run to play a massive role. And that actually, I say this because it addresses another question that came up about should hydrogen be viewed as a stepping stone in the energy transition or energy transitions, depending on how you want to say it, in different places around the world, or should it be viewed more as something that's integral to a lower carbon future and sustainable in the long run?
The answer is both, I would say. And it depends also, again, the color, right? So I would see blue hydrogen as a stepping stone towards a hydrogen economy, while the green's catching up fairly quickly. You would see, as we see, cost of electrolyzers and also the cost of renewable electricity coming down around the world, you would actually see a lot of hydrogen becoming an important part of the energy mix as well. I always want to highlight this point that you always are going to have an energy mix, right? It's not going to be just one. You would have electrons, you would have fuel as also part of energy mix, and you will also have hydrogen playing in the energy mix. How that composition looks like would change according to the geography, would change according to the evolution of technologies. We can speculate at this time, but there are going to be breakthroughs over the next decade, which would probably what looks like an energy mix right now might not be the same at the end of the decade. But we are seeing signs of tremendous progress, as you said, in terms of using the existing infrastructure, how to leverage existing infrastructure to produce cleaner fuels, but also new technologies coming up.
Yeah, I think so that point is actually a very critical one that I think is often underappreciated. But there's this concept that's referred to as the valley of death for energy technologies, right? And one of the interesting things we see through history is the technologies that can integrate them with the least amount of issue with existing infrastructures, with legacy capital assets. Those are the ones that tended to be the most successful and have the biggest impact. Whereas a technology that requires you to replumb the entire system because of the support cost and the infrastructure associated with it is likely not going to really be that successful. It's going to fall into that proverbial valley of death. And hydrogen, in many ways, checks all the right boxes because you can leverage existing infrastructure. You can, transition assets in a staged way. It doesn't have to be all or nothing. And it does allow for diversity, which is another really critical point because the energy mix today, it doesn't look like it did 50 years ago, and 50 years from now, it won't look the same as it does today. And that's largely because of infrastructure investments, economic development in different parts of the world, comparative advantages being leveraged in different parts of the world. I mean, it's going to be different everywhere. So I think that's actually a really, really critical point. So you and I had talked previously, and I'd love for you to kind of dive into this and expand on what I just said through this. But we talked previously about, basically thinking about hydrogen and just energy transitions in general using 5 I's, right? I would love for you to elaborate on that because I know it will connect with a lot of the viewers, I think. So I'd love for you to just dive into that real quickly.
Well, thank you. So whenever you think about any energy transition, I think you have to think about it in 5 I's, as I say. The first one is the innovation, right? So that kind of covers the technology development part of it, which we just talked about. There are technology gaps, which would be addressed primarily by innovation. And the next Silicon Valley, Houston can be the Silicon Valley for energy transition that way, right? Because we do have the right skill sets. We have entrepreneurs. We have students and world-class universities like Rice University, where we can drive innovations. We have several different accelerators coming up into Houston in terms of energy. You have Greentown Labs, you have the ION. So these are examples that I'm quoting because this is going to be a fertile ground, and innovation is going to be key for energy transition because as you prefaced this fireside chat, is some of the technologies that would be part of energy transition do not exist as of today, right? We have the other one that I would say is the integration. The other I is the integration. The integration, as I said, is again, we talked about it in terms of how different sectors would couple. Any solution any technology that comes up has to be flexible enough to address multiple parts of the energy demand side, not only just power, but also transportation and industrial and commercial and residential requirements. So it's not just putting fuel in your car or turning on a light in your drawing room, right? It goes beyond that. Energy is beyond that, and so integration and hydrogen actually plays an important role in sector coupling. The third I is actually critical, and that's what has brought the change here, is the investment that's required, right? And the the proverbial, or I would say hypothetical hype. I don't know how to put it, because some people like to say that there's a hype around hydrogen, but it's not a hype, because the market in general is quite activated towards the climate imperative. And the investments are actually what's driving the innovation, and also will enable the integration. The fourth I is about the information, right? So there exists a lot of misconception about energy transition, about different ways to decarbonize, and not necessarily everyone is educated the same way. Even the policymakers at times, right? So there is also a responsibility on behalf of technology developers to not only educate the public, the end user, but also educate the policymakers so that the policy is made in the right way to enable the right kind of development. The other part of this information sector is about the safety aspect of it, right? Safety is very critical when a new technology comes into place, and so there is a responsibility on part of the technology developers to understand and also inform about the safety. For example, there's a lot of misconception about hydrogen. The reason I say that in the beginning I said that we know how to handle hydrogen is, if you go on social media, there's a lot of information about how hydrogen is explosive, and even sawdust, for that matter, is explosive, if you don't handle it properly. So that way, the misinformation and lack of information has to be addressed. The fifth I is the intention, as I call it, and this largely covers the policy aspect of it. What is the intention of that particular country, particular geography, particular location to bring about the energy transition? How do they think about it? And that has to be inclusive, because any energy transition has to provide the socioeconomic benefits. You can't overnight turn from one system to another system, and you have to do it in the least impactful way in terms of affecting people's livelihood and safety of general public. So that is another I. So there's 5 I's. So one of the takeaways from this fireside chat is, if you think about energy transition, think about the 5 I's: innovation, integration, information, investment, and intention. So I would say that kind of covers the whole gamut about energy transition talk.
Great, yeah. So the reason I wanted you to dive into those is because it pulls up a couple questions I wanted to ask you, because I think they're critically important for success at the end of the day. One of which is affordability. And I would love for you to talk a little bit about what the industry is doing to ensure affordability as we move through these energy transitions, and what role will hydrogen ultimately play in that? Capital intensity matters when we're talking about affordability. A lot of people want to focus only on variable cost of operating certain assets, but we know that because of investment and investment requirements, the all-in cost matters, right? So the capital intensity of the venture matters as well. So I wonder if you could address that briefly.
Yeah, so that's actually a very critical part, right? Techno-economic feasibility. You might have the best technology that works in a laboratory, but if you cannot bring it at scale and produce, because at the end of the day, it is a commodity product, that goes into the market. And if people cannot afford it, it doesn't make sense. And so, for example, I'll just give you an example in terms of green hydrogen, because it's kind of easier to visualize how innovation as well as policy and investment come together here to address that particular part, right? So 2 important cost factors when you think about green hydrogen production. One is the cost of electricity itself, renewable electricity. And the other one is the capital expenditure for the electrolyzers, right? So right now, electricity in terms of cost reduction, the cost curves have come down tremendously partially because it was supported through public money in between. And once it became at scale, it was able to sustain itself, right? So and that way you addressed one part of the cost curve. The second part of the cost curve is right now under a lot of research and development, I would say, in terms of how to reduce the cost of electrolyzer stacks. And there are several different companies that are actively working on this. This is one of the hot areas of research. And it's not just, one component of the electrolyzer. It's not just the expensive metal that you're using in the electrolyzer. It's the overall cost of implementation and scalability. And once the technology is deployed at scale, the cost comes down. As a rule, right? So there has to be investment to be able to have large scale deployments for this. So ACE's project, for example, ACE's project is one such avenue where we are having a large-scale deployment of electrolyzers, right? So we would see the cost curves coming down in terms of large-scale production of green hydrogen. That's just an example. But I hope I answered your question in saying the different parts of the cost curves, and it is where both policy, investment, and technology development has to take place simultaneously to reduce this.
Yeah, so that's a great way to put it, because when you're talking about really trying to accelerate transitions, the role that policy plays is critical in incentivizing the appropriate investment so that you can bring things to market at scale. So I think is another way to say that. And that kind of speaks to another thing I wanted to ask you about, which was collaboration. So between industrial actors, between governments and industry, between academia and industry, all of the above. I mean, we see that at play in Houston, for example. I mentioned all the different groups that are looking at different hydrogen pathways, and there's an effort ongoing to create more collaboration amongst those groups, because everybody has something to offer, and painting a cleaner picture means everybody's talking to each other at least, right? So I think it would be useful for you to share kind of through your own experience, through MHI's experience, how collaboration has helped you to get some of these projects off the ground, and how you think that's going to play a role going forward.
Yeah, so collaboration is actually the key for energy transition. One player cannot do it on their own, and it might sound a little cheeky to say this, but we are all competing against time. We're not competing against each other from the climate imperative perspective, right? And from MHI side, we have, if you look at the energy, if you look at the hydrogen, for example, hydrogen value chain, we have products that use hydrogen, right? But we didn't have until now for some time things that address the upstream side of the value chain. So the way we did it is two ways. One is we went in and made investments in startup companies and developed that, fill that lacuna in the value chain. But we are also actively involved with industry partners. For example, I mentioned that Chevron is part of the ACES project. We are also part of the H2 at scale. That's a very good example where not just industry but academia. UT Austin is one of the leads, and then Gas Technology Institute is leading this effort of actually there are two folds of the project. One is looking at decarbonization of Port of Houston as a hydrogen hub, and also trying to demonstrate use of hydrogen at UT Austin to look at a data center, right, to power a data center. So this is an excellent example of where government, because it's funded by DOE, and academia partners, UT, UH, and then also you have several different industry partners participating in this. This is just one of the examples. If you see around the globe, for example, the Hystra project, right, where they're looking at hydrogen being transported from Australia to Japan, you have several different players, and it's you have Shell, you have Kawasaki, you have MHI. So all these, it is not. We all bring our own technology strength to the table, and the combination is what will result in a very optimal solution, so to speak. And that's me being very, very optimistic in terms of how this whole thing will play out. But it's very evident that we cannot go on our own, but have to collaborate and extensively. And we are seeing examples of this all over the world, not just in the United States or Texas.
Right. So there's been a few questions come in that I think I'm going to try to weave into a frame that really speaks to the manner in which hydrogen markets in general will develop. So in many ways, you need demand pull, right? This isn't a build it and they will come kind of discussion, right? You can talk about, massive capital expenditures on tons of electrolyzers and generating all sorts of green hydrogen and storing it in salt caverns and using it for what, right? That's kind of the next question, right? It's and in many ways, I think this has a lot to do with why, what you referred to before with regard to hydrogen really fueling the vehicle of the future, which was the wave in the early 2000s, under the then Bush administration and the emphasis that was placed there, and GM diving all in, on fuel cells. And we saw companies like Toyota go with hybrid model, and that tended to win the day, right? And it was kind of easy to figure out why. It just leveraged existing technology and existing infrastructure. So when you think about hydrogen going forward, I think sometimes people go back to that mindset and they think immediately of, well, it's about personal transport. Well, in reality, a lot of the stuff that you just referred to, like at Port Houston and some of the big industrials, they're not looking at it for personal transport. They're looking at it for freight movement. That's definitely true. But they're also looking at it for, industrial heating is an industrial fuel. And that can bring scale very quickly to the market, right? And that can allow some of these smaller things to develop in almost an ancillary way to the extent that they develop, right, without having to mandate a certain type of demand pull. So I wonder if you could maybe talk a little bit about that. You and I have chatted a little bit about this in the past, but I wonder what your views are on how you think this market will ultimately evolve.
Yeah, I think you answered most of most of the question yourself, and thank you for doing so, because it kind of makes my job easy now. But as I said, the near-term application of hydrogen, as we see it, is in first of all, balancing of power, right? Balancing of power, curtailed electricity. The other one would be to look at industrial heating, and then, as I said, sustainable aviation fuel, right? Hydrogen as a feedstock for that. In steel industries, the hard to decarbonize sectors like shipping and aviation and stranded, heavy duty trucks, drayage trucks around Port of Houston, forklifts that run on fuel cells. So these are examples that would actually bring hydrogen to scale fairly quickly, especially in industrial hubs around the world, like Houston. You can think about Port of LA. They have a very big program around decarbonization. Corpus Christi, as well as several places in Europe. A lot of them in UK, Teesside, for example, where and Hamburg in Germany, where these solutions are being looked at, and then that would bring it to scale fairly quickly. But these are the near-term applications, not just personal transport vehicles. Yeah.
Yeah. So I'm glad you mentioned other areas largely around ports, because, and for those of you who don't know, we actually have an energy and transportation program where we actually do an annual summit now, the first of which was last year. The next one's scheduled for later this spring. But we focus on freight and heavy transportation, and that usually means a lot of development around ports. And it's kind of funny because when we dove into this, it took me back to my dissertation days when I quickly realized I was looking at energy and economic development. Ports are very much the canaries in the coal mine when it comes to what's about to happen in a particular region. So seeing this happen in different places is a really interesting development, and I think foretelling of what's coming down the pipe. Pradeep, we're up against it on time. For those of you who had questions we didn't get to, I'm sorry. We've got a log though, and we'll try to reply to you in due course. And as Pradeep mentioned, if you have a specific question for him, feel free to reach out, and we'll make sure that you get connected. But thank you very much for joining us today. Really appreciate the conversation. And to everybody else, stay safe and stay healthy, and hope to see you soon.
Thank you very much, Ken. Thank you for having me, and thank you to the audience for participating.
Absolutely.